In this video, we're going to look at strategies that can help you be successful on roadmap type questions. To begin with, when you look at any reaction, whether it be a single note card type reaction or a series of reactions in an overall synthetic scheme, you want to identify electrophiles and nucleophiles. Use the bonding patterns such as the carbonyl or Grignard to identify something that can accept electrons through a reaction or donate electrons in a chemical reaction. Once you identify your electrophile and nucleophiles, you can then determine the reaction type. Is this a Grignard reaction? Is this a hydride addition? Is this a Wittig? To reinforce this type of reaction identification and identification of electrophiles and nucleophiles, you're going to want to practice your note card reactions. That helps you build your vocabulary. These first three are fundamental to being able to work on roadmap type questions. Additional strategies are count carbons. That is, how many carbons are in your two reactants, and do you have the sum of those two numbers in your resulting product? You can highlight bonding changes, that is, identify how a molecule was changed through a chemical reaction. You can work forward and backward. You can use blinders to focus on a single reaction. That is, cover up the rest of the roadmap and look at a reaction as if it's a single note card. And then the last thing that we'll talk about is looking for similar reactions elsewhere in the roadmap. That is, do we find any hints or clues that might be useful? Here is a representative roadmap. This allows us to talk through these different strategies using a concrete example. So what we want to do then is say, okay, if I look at my starting reactant at the very top left, the only kind of reaction type that I can imagine is looking at this aldehyde and saying this looks an awful lot like an electrophile that we've been talking about. So if I have an electrophile as one reactant, I know that whatever it reacts with, that is the thing in the box, must be a nucleophile. So by identifying the electrophile and the nucleophile, I now have narrowed down the possible kinds of things that might show up in here. In order to pick it apart, what I'm going to do is figure out where the bonding, the new bonding takes place. So if I walk along the backbone, I see I've got a double bond, I've got this protected oxygen, I've got a couple of CH2s, and then I get to this carbon that in my starting material was a carbon double bonded to an oxygen. Now it's single bonded. And so I'm going to look at that new bond here between the alcohol carbon and the carbon alpha to the phosphonate, and say, okay, that's where the change took place. Let's go ahead and see about changing pen color. I think that'll make this better. So let me use the barbells here to illustrate. That's the new bond that was formed, which means that my nucleophile has to come from these components, because this portion of the molecule was my electrophilic portion. So if I just take and copy these over, I know that I'm going to need this anion here adjacent to the phosphorus. So when we were working on this, we looked for electrophiles and nucleophiles. We looked at highlighting or identifying the bonding changes. Now let's go ahead and count carbons. Let's see how that works. So I've got 2 carbons being added in this one, and I'm adding that to 1, 2, 3, 4, 5, 6 in the backbone. So if I add those up, 1, 2, 3, 4, 5, 6, 7, 8. I have an 8 carbon chain And that matches with the 2 plus 6. So I've used the counting carbons to verify that the amount of carbons that I added with my nucleophile matches with what ends up being transferred into the product if we just look at the bonding change and how that adjusted the carbon backbone. Now we can move on to the next reaction. Here, I have a 1, 2, 3, 4, 5, 6, 7 carbon backbone. So we'll just go ahead and start counting that, 7 Cs. And then I've got 1, 2 Cs in this. So that means that in the end, I'm going to have a 9 carbon chain. If I look for my electrophile and my nucleophile, again, I've got an electrophilic atom here in the carbon attached to the oxygen in the aldehyde functional group. And then here, this must be my nucleophile. And this is a Wittig reagent, or Horner-Wadsworth-Emmons reagent. And that means that I'm going to want to draw a resonance structure of that to reveal where my nucleophilic atom is. So I have my ylid with my nucleophilic atom right here. And so what I'm going to need to do is then connect that. And so I can draw that mechanism, electron pushing arrow, identifying how the first step is going to proceed. Because we're not asked to draw the mechanism in roadmaps, what I need to do then is remember that at the end of this, I'm going to end up with an alkene. And so if we draw this in, I'm going to draw and here's where watching your stereochemistry can be helpful. Using these as labels is quite useful. And I have it drawn in. Now, how did I know how to draw this in the E orientation rather than the Z? And what I did is I looked forward. Again, working forward and backwards can be helpful, and we can see that here we have the E orientation here where the carboxylic acid and the rest of the chain are on the opposite sides of the alkene. So I drew my ester here that undergoes hydrolysis. Now, here's an example of working backwards. On top of this is not only looking at the geometry of the alkene, but also thinking about what would have happened if I thought backwards. Lithium hydroxide and water and THF are good conditions for transforming an ester, which I had in my starting material up here, to a carboxylic acid. So I could have simply redrawn all of this in the box and then changed the carboxylic acid component to the ester. In all of these boxes, we could have simply zoomed in. And so let's do that right now. So what I'm going to do is take and draw a box around this third reaction that we're going to talk about. And this is what we refer to as putting on the blinders. What we would do is we would cover up the rest of the reactions surrounding this box segment of the roadmap with Post-it notes. It's a great way to sort of obscure the view so that you're not worried about what else is going on. You can draw your attention. This is particularly useful as the molecules get more complicated. Look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons on this backbone plus an ester oxygen. with all of these methyl groups and protected alcohol and a phosphonate ester. There's a lot going on in this molecule. And so by blinding or removing the distractions using Post-it notes can really help us zoom in and focus on what's going on. Now, when we look at what's going on here, what we want to do is say, what's happening? Because I know that I have an electrophile here. I have an electrophile here. I've got a not as good electrophile on this carbonyl carbon. And so this is where moving forward and backward, thinking about what's going on around it can be somewhat useful. And that's where if we look at the product, we're going to see that the new thing, and I'm going to use these barbells to illustrate it, we formed an alkene. And we did that before in a related situation where we saw the formation of this alkene over here. And so this was using a Wittig type approach. And so we're likely going to be seeing something similar. And you'll notice that it also forms a ring. That means that my nucleophile has to be present. And so if we just count around, and I'll start from this end of the alkene, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms around. This has to become my nucleophile. So this, as it stands, is not presently a nucleophile because it still has the proton, which means I need to add a base. And so here I could use a variety of bases. Because it's alpha to both the phosphonate and a carbonyl, I can use a relatively weak base. But I'm worried about hydrolyzing the ester down here, so I might choose to use something like sodium hydride. To deprotonate at this carbon, this is our most acidic proton throughout the entire molecule. It allows us to form the new bond between this carbon and the aldehyde carbon, and then through the reaction mechanism give us this alkene. Now we move on to the last box. And again, what we want to do is think about what has changed. And so if we look at this this 14-membered macrocycle, and we compare it to what's going on up here, our eyes are drawn toward the top where we see in the starting material we have a carbon-oxygen double bond, in this case an enone. And now we have an allylic alcohol where if we draw in the hydrogen, we now know that we have to form this new bond. So I'll use the dumbbell and illustrate that. And so we need to have a hydride that will be selective for this carbonyl carbon and not anything else in the molecule. If we used LAH, that would go crazy and hit both the ester and the ketone. And so we want to use a milder version. And so we're going to use sodium borohydride.